Welcome to the course on advanced power electronics. We'll cover today topic on multipulse converters. Now coming to multipulse AC/DC converter for bidirectional power flow. Actional power flow means first coming to full wave. So here it is a full wave 12 pulse isolated with the thyristor converter. These are used for high current, low power, typically for like electroplating, electromining, where the voltage is 20 to 40 volt, but the current is quite high kilo ampere. So there it becomes important that you use the full wave. And this is for your 18 pulse full wave. How we are getting a phase shift? 18 phase we are getting like a 20 degree phase shift. Then the 24 pulse, how we are getting 24 pulse from here, 360 by typical 24 phase are derived. So it's a 15 degree comes between the two phases. And this is another 12 pulse converter, full wave. Now coming to bidirectional multipulse bridge converter. So this is again the 12 pulse. With that you can call it isolated T connection. You are able to get a phase shift of 0 to 30 degree with the two converter. And here is another set with the star delta connection. This is another interesting connection of control converter where you have your typically the supply, and then you have here pulse doubling also here. 3 times pulse we are able to increase of 6 pulse here with the help of this. And this is again 24 pulse where we are putting 4 bridge of 15 degree phase shift on the secondary with the zigzag your extended delta connection. The another side with the pulse doubling from 12 pulse isolated control converter with the 3 times pulse multiplication, and we are able to get 12 into 3 means 36 pulse. Similarly 48 we are from 12 pulse we are able to get a 4 times with the 4 thyristor. So it will also become very interesting that 40 with the your 16 thyristor you are able to get a performance of your 48 pulse with this converter. Then you have a typical 12 pulse bridge. So we derive it here also 15 plus minus 15 degree 30 degree phase shift, and then from your low kV rating PM half bridge is able to save the current to sinusoidal. This is another case of 12 pulse typically converter, and then the 18 pulse converter, control converter. Now coming to analysis and multipulse diode thyristor rectifier. So this is like you can say 12 pulse, 18 pulse and 24 pulse. How many converters are used in this isolated topology? And this is the first like a 12 pulse rectifier with the phase shift of 30 degree. So series type 2 6 pulse rectifiers are used in series output, and phase shifting is provided 30 degree. Here you can see how it is provided. And then the secondary line voltage VAB by 2 and turns ratio N1 to 2 and 1 by N3 2 by root 3. This is another 12 pulse connection with the diode rectifier with the series connection in the output. You don't need the interface transformer. So in 12 pulse series type of this waveform, you can see how the 1 6 pulse and phase shift is second, and then the total net current of supply, how the TID reduces from 21.4% into converter of 6 pulse, and it cancel out for 18. Your TID of supply current becomes 8.38%. So number 5 and 7th harmonics are in the line current. Primary line current TID is 8.38%. Coming to 12 pulse series type of diode rectifier, total amount of harmonic distortion and the power factor, how it is reducing with the source impedance, you can clearly see here. Typically the power factor is also a little bit affected. So conversion of 6 pulse TID is reduced and the power improved. This is your 18 pulse converter where 3 converters are connected in series with the proper phase shift of plus minus 20 degree. With the isolation we have to put transformer, so with that serving purpose. And this is you can see how the plus minus 20 degree and a main converter is there, and the net current sum of this go to the output which go closer to sine wave. So individual bridge is having TID 23.7% because of source impedance, and the net TID for typically your 18 pulse it comes 3.06%. So that's it. Typically you can call it how the 713 are elemented. The lowest will be the 15th. So now coming to measured waveform, these are experimental waveform, how really it improve 6 pulse to 12 pulse, and how the TID and power factor varying with the source impedance. Then coming to 24 pulse converters, 4 converters are connected in series. You can connect in series also with because isolation with the plus minus 15 degree phase shift is given. and plus minus 30 degree. So typically waveform are there of all four converters, and you combine it becomes like a TAD. Each converter have a 24% TAD, but TAD of supply current is your 1.45%. The lowest TAD of 23rd. Now coming to TAD power factor, it's also affected the Y source impedance. Then coming to 12 pulse rectifier with isolated load and separate, each pulse feed a separate load. This is your typically very famous multi-level edge bridge fed bridge drive, which is also called sometimes your Rubicon drive, which is taken over Allen Bradley. So they use this kind of configuration. So there is a challenge of design of converter rectifier as well as of inverter side. And this is waveform of supply current. Then say 6 pulse, then phase shifted, then net, and the TAD at the end you will find it's at 7.36%. So that's now coming to separate type. So measured current, experimentally you can see how really it is improved, very low TAD, and how it is affected by the source impedance. So now coming to 18 pulse, we have a 3 bridge splitting separate load, and with plus minus 20 degree because of zigzag connection, and in between is the 30 degree without phase shift. So we get the 3 equivalent load, and we get a waveform corresponding to this for all 3, and net current waveform with 3%, 3.05% TAD. Now coming to line current power factor, so how it is really affected by source impedance here also, both the parameters, and then other 24 pulse converter. Now coming to 24 control converter, thyristor converter, again phase shift of plus minus 15 degree, and output connected in series like HVDC to give 12 pulse. So main benefit, line current TAD is reduced and no SCR in series. And this example is 12 pulse converter feeding your your current source converter. So here in supply current harmonic चालू used for current source fed drive PWM die, and how the supply current improve from 6 pulse to 6 pulse and finally 12 pulse drive. So coming to Fourier series, this is a Fourier series from one 6 pulse and another 6 pulse, and then typically the net. So net you will find by adding, you will find primary current, your 11th is the lowest and 13th, then another band of 23, 24. Now coming to line current TAD here for 12 pulse, I1 is divided by I1, so it comes typically order of your 15%. And here in primary side it goes to 15%. So, and with the zero source impedance, how it is really, and with the source impedance, the TAD reduces to 24.6% to 8.61%. And this is how it is affect source impedance, the TAD as well as power factor. Now coming to 18 pulse converter, in 18 pulse also you can see how the 3 bridge currents and net current, and the TAD reduces from individual bridge from 24.6% to 3.54%. Coming to line current TAD, how it is reduces typically the source impedance. Coming to 24 pulse converter, where both thyristor converter are connected in series, so you have to use interface transformer. Imagine star, of course, phase shift is plus minus 15 degree. So line current here TAD also affected by source impedance. Now coming to analysis of isolated 4 connected transformer based AC/DC converter, so you can see how really typically your delta star and 6 pulse converter, and how your work phase your 12 pulse converter with of course typically your interface in parallel. If you are connecting in parallel, you have to use interface, but in series you not to use the interface. So 24 pulse converter for 4 base connection. How it is the design? Typically with the phase shift providing for 24 plus minus 15 degree plus minus 75 degree plus minus 15 degree. And this is the analysis to do design calculation of all the data and rating, how you calculate. So rating is also typically goes little higher for isolated. This is a model, MATLAB model of this, and this is the performance, how really your ripple factor reduces, and TAD of supply current also reduces from your 10% to with the load 9 point and 12 to 4.46 to 2.7%. And then typically here again comparison 12 pulse for 24 pulse, and at full load you can see for 6 pulse 24%, and 12 pulse it's 9.24%, 24 is a 2.7%. And these are typically the rating. How it is rating have to be more than 100. The reason being simple, because of course isolation itself 100%, then you have to use some of the winding might be secondary, might be having harmonic current flowing through that reduces RMS current in that. So this is another delta for this 36 pulse converter. We derive typically again here 36.2 your 9 phase that give 18 pulse and 2 sets. With the interface we get 36 pulse. And this is the design for your, you can call it the 9, your typically getting a your 9 phase, and then the accordingly correspondingly here and design calculation MATLAB model and the performance of really how for TSD reduces in this case 36 from 3% to 1.17%. Such low TSD require normally naval application, and then your comparison to, of course, with the your topology of 3662 and how the winding currents, different portion of winding of 36 pulse converter flows into a net supply current addition of all. And then the typically at light load 3% TSD and at load typically 1.197%, and these are experimental. For light load 2.3% TSD, and but power factor is almost unity, and TSD light load 2%, and the rating of experimentally and the performance. Now coming to analysis, T-connected isolated transformer based AC/DC converter. This is your, you can solid T-connected, how really having a 6 pulse converter bridge, and then the waveform, how addition of different waveform and how the TSD 20, then 12 pulse T-connected, 2 sets of 3 phase, then the pulse doubling for to make 24 pulse, and how this design for interphase and modeling of it, and the TSD of 6.1% 12 pulse and 24 pulse it goes 3.5%. This is of course the performance of 12 pulse 18 pulse, so you can see supply current TSD reduces 3.5%, and then the 24 comparison up to 24. Now coming to unconventional multipulse converter. Unconventional means they are not multiple of 6 like common. So in that case we convert like a typically here unconventional multiphase is like non-isolated, then hybrid of phase staggering and multipulse for deriving like a 12 pulse, 28 pulse, 44 pulse. So we convert like a typically 3 phase to 5 phase, and then 5 phase give a 10 pulse, another phase is staggered give a 5 phase, so total become 20 pulse. Similarly 3 phase is converted to 7 phase, and from 7 phase one set comes your 14 pulse, another set 20 pulse, it becomes your 28 pulse. Similarly we convert 3 phase to 11 phase, and then we have a phase shift. So 11 phase give a 22 pulse, and then 2 sets of 24 with the interphase we get the 44. And hybrid of all 3 concept, phase staggering, multi-phase and ripple injection or pulse doubling. So that to then pulse doubling, this 24 pulse 20 pulse give 40 pulse double pulse, and 28 pulse give a 56 pulse, and that 44 pulse give a with pulse ripple injection and pulse doubling it give 80 pulse. So coming to 20 and 40 pulse converter, so this here we are deriving a 3 phase, a 2 sets of 5 phase with the phase shifting. Because in 24 pulse we should get a 360 by 20, that kind of phase shift. So that comes 18 degree. So accordingly we design 2 sets and with the interface transformer. So this is the providing the phase shift for 20 pulse and the T connection transformer, how we really design for the then 18 degree phase shift, for different segment of winding. And then these are the typical design for 40 pulse converter with the winding tappings and all coefficient design. And these comes like a large number of coefficient with the for calculating the design of different segments of the winding. So you get typically a large number of segments as you see here, typically 13 segment with the different these K1, K2 represent the times the phase winding voltage, and then the typically for your single polygon of dual 5 phase, how 2 connection, then of course performance evaluation. So we get this for typically 40 pulse, how we get a supply current sinusoidal even during induction motor drive feeding for starting then load change, but supply current remain exactly sinusoidal in phase with the supply voltage. So TAD of course for 24 pulse it come 5.52%, and 40 pulse it come 2.2 to 6%. And then you can have a comparison of the TAD from 6 pulse 62 to coming to 20 pulse 5.52, and then 40 pulse it come 3.85. And these are typically, you can see the photograph of 40 pulse configuration which are developed in laboratory by our research student, and the TAD you can say how really it's reducing from 4.6% to 1.5% per load for 21, and for 40 pulse 2.7 to 2.2%. And then the rating of the transformer magnetic rating, the non-isolated it comes less than 100%, 56 or 40%. And then the TAD experimentally get TAD of really 2.7% of supply current at light load, and full load is 2.7%, not much change. Three-phase supply current with the voltage and supply voltage, supply current, DC link voltage, DC current, and then your experimental isolated 40 pulse, the TAD, how it is go 2.53%, and how there is a drastic improvement 20 pulse to 6 or 40 pulse, the TAD reduction to almost to half. Now coming to 28 to 56 pulse AC/DC converter. So here we convert 3-phase into 7-phase. 7-phase, one set of 7-phase give 14 pulse, and with the phase staggering it give another 14 pulse, and combined together get the 28 pulse. And of course with the pulse doubling we are able to get 56 pulse. So 14, 14, 28 into 2, 56 pulse. And this is the design, of course, how we get the 3-phase to 7-phase, 2 sets of 7-phase, and these are the winding typically segments. You can get 16 segment for 56 pulse transformer, and how the winding segments and design, pulse doubling design there, and the different angle, phase shift angle correspond to that, and all the winding design here typically for this your 7-phase to 14 pulse and 56 pulse also. So all the so many segments are there, and you can see all segment 16 segment value deriving from simple geometry we get there. Now coming to performance evaluation of this 28 and 56 pulse converter. So here you can just see how the 56 pulse converter supply current even during motoring starting and load change, and then the TAD comes 2.41%, and then you can see how it is varying from 6 pulse to 28 pulse 5.4 and 2.41% to 56, and yearly experimental TAD of your this 56 comes 2.6%, and from TAD of your 28 to 56 pulse, which reduces to almost half. And this is the design typically of your transformer isolated, and how the different winding currents and summation of all 56, and the TAD reduces to around 1.218% for this 56, and then the typically your harmonic distortion. Coming to now 44 and 88 pulse converter. In your 44 pulse we convert 3-phase into 11-phase. 11-phase give 22 4 pulse. With pulse phase shifting we get the 2 sets of 22 pulse, and then adding together it goes 44, and pulse doubling it gives the 18 pulse. So this is the design of the different phase shift, how we are getting a phase shift, and TAD for this 44 comes 3.85%, and TAD of typically your at full load, and this is the 88 up to what we get from typically up to 1 to 6 only, so remain less than 1.5% in 88 pulse, and 44 pulses to remain less than 3%. And then the typically how for different isolated rating of magnetic and for. So now coming to sold example, numerical examples. So example 1, a DC load of 1.2 kilovolt, 500 ampere is supplied by a 12 pulse thyristor bridge rectifier at a 30-degree firing angle of the thyristor. So calculate a required thyristor rating, and typically transformer secondary voltage with primary applied 3-phase supply voltage of 415 volt at 50 Hz for series connection of two thyristor bridges. AB current in each winding of the transformer, the kVA rating, and supply current, D supply current, and its TAD. So this is typically 12 pulse, the control rectifier, delta to star delta, and series connection, does not need interface transformer. And coming to solution, given supply voltage VLL equal to 415 volt, frequency of supply 50 Hz, DC load current is 500 ampere, and DC load voltage is 1.2 kilovolt. So total DC voltage across series connected thyristor bridge is 1.2. So the DC voltage across single thyristor bridge is 1.2 divided by 2.6 volt or 600 volt, and average output voltage of one thyristor bridge will be DC1, that is 3 root 2 upon pi into VL cos alpha. So from here we get typically considering cos alpha 0, so we get 30 degree, so we get a VL equal to 13.019 per volt, and then the VL is the line voltage of the secondary side of transformer, and the secondary side of transformer is connected to star, so the phase voltage of the secondary side or VLN equal to 296.19 volt, and thyristor PIV rated to VLL, that's a 725.51 volt. The secondary side transformer connected in delta, so the phase voltage of secondary side is VLN equal to 513.019 volt, and the line current of secondary side transformer is as root 2 by 3 ID, that becomes 408.24 ampere, and the line current of secondary side of delta transformer IL equal to root under root 2 by 3 into ID, that comes 408 2 ampere, and the phase current of that secondary side delta, so that delta is 408.24 divided by root 3, 235.69, and from transformer is N1 to N2, 15 by pi 13 and divided by root 3, that comes 1.401, and transformer turns ratio N1 upon N3 comes 415 divided by pi 13, so 0.8089. And these are the typical current, supply voltage, supply current, then the two converter currents, the net orient current, and DC link voltage and DC link current. And the supply current from this waveform you can find out the primary, adding primary and secondary together of delta and star. So primary comes 1976.58 and kV rating 0.5 into 3 into PLN IPH. So putting value it comes 713.726 kVA, and the idea of harmonic distortion adding all the harmonic up to 49 it comes 15.23%. Now coming to example 2, a DC load of 1500 volt 300 ampere is applying 18 by an 18 pulse bridge rectifier. Only calculate the required diode rating and transformer secondary voltage with primary applied 3-phase supply voltage of 415 volt at 50 Hz for series connection of 6 pulse converter, aligning the current in each winding of the transformer, the kV rating of the transformer, and D the supply RMS current and STAD. So this is 18 pulse converter, so you have to give a phase shift of again 20 degree. So one is with the zigzag 7.5, another two is again plus minus 18 degree, so 77.5 and then minus 12.5, and connection in series, so interface transformer are not required. So given supply voltage VLL equal to 415 volt, frequency of supply 50 Hz, DC load current is 300 ampere, and DC voltage is 1500 volt, and total DC voltage across series connection diode bridge rectifier is 1500 volts. So the DC voltage across single diode bridge is 1500 by 3, that is 500. So average output voltage of each diode DC equal to 3 root 2 pi upon VLZ. So by putting a VLZ comes equal to 370.2 volt, and VLZ is the line voltage of secondary side of transformer. So diode rating BIV root 3 VLZ, so that is 523.59, and secondary zigzag transformer connection I root 3 by I to under root by under root 3 ID, that becomes 244.94 ampere, and transformer turns ratio N1 upon N2, 239.6 divided by 213.6, that become 1.12172. Transformer turns ratio of second N1 upon N3, 239.6 upon 13.6, 1.12172, and 1 by N4, that's also come to 39, 1.12172. And these are the typically 3-phase supply voltage, supply current, then your 1-phase current, and then your one transformer, and then the DC link voltage, DC link current. And now calculating the primary current, adding of N2 upon N1 ISPZ plus N2 upon N1 ISPZ and N4 upon N1 ISPZ. So putting a value, it comes IPLY equal to 628.746 ampere, and kV rating of transformer is 0.5 into 3 into VLN into ILN. So putting value, it comes 461.5 kVA, and the idea of supply current adding up to 73 harmonic. 70 is minimum because of 18 pulse, so it comes 10.09%. So coming to example 3, a DC load of 2.4 kilovolt 100 ampere is supplied by 24 pulse diode bridge rectifier as shown in figure. To calculate A, required diodes rating and transformer secondary voltage and primary applied 3-phase supply voltage of 460 volt at 50 Hz for series connection of converter. B, the current in each winding of the transformer. C, the kV rating of transformer, and D, the supply RMS current and its total harmonic distortion. Now this is just typically 24 pulse converter with a zigzag. You get a phase shift of 20 to 15 degree from 7 plus minus 7.5 and plus minus 22.5, and all diode bridges are connected in series, so that makes the no need of interface transformer. So coming to the solution, given that DC load current is 100 ampere, DC link voltage is 2400 volt, primary 3-phase current, primary voltage 460 volt, and frequency 50 Hz. The total DC voltage across series connected diode bridge rectifier 2.4 kilovolt. So the DC voltage across diode bridge is 2.4 divided by 4, 600 volt, and average output voltage of one diode bridge rectifier is your VDC1 equal to 3 into root 2 upon pi VLZ, and putting a value VLZ comes to 444.2882 volt. So VLZ is a line voltage, so diode rating is root 2 VLZ 628.31, and secondary zigzag transformer current is ISZ equal to root 2 by 3 SD, that comes 81.64 ampere, the transformer turns ratio N1 upon N2, it comes to 265.58 divided by 256.50, it comes 1.0333536, that is equivalent to N1 upon N3 and 1 upon N4 and 1 upon N5. And this is a simulated waveform from supply voltage, then supply current, one page current, then the one bridge current, then the DC link current and DC link voltage. So coming to the supply current, RMS current for primary side, so IPPD is N2 upon N1, IPZ 22.5 and 3 upon N1, I 7.5 and plus N4 upon N1, IPZ minus 7.5 and 5 upon N1, IPZ minus 22.5. So it comes to 302.052 at the angle of 0 degree. So KV rating is 0.5 times 3 VLN and KN, and putting the value, it comes to 45.977 kV, and TID of harmonic cord, or let's say adding all harmonic 23 to 97 upon I1, and this comes 7.57%. Now coming to example 4, a DC load of 3 kV 150 ampere is supplied by a 30 pulse bridge rectifier as shown in the figure. Calculate a required diode rating and transformer secondary voltage with primary applied 3-phase supply voltage of 440 volt at 50 Hz for both series connection of 6 pulse converter, the current in each phase winding of the transformer, the kV rating of the transformer, and D the supply current and T is TID. So this is your typically a 30 pulse converter, 6 bridges are connected in series, so 5 bridges connected in series for 30 pulse, so your 60 by 5, that's a 12 degree. So you can say here one is of course your 4.5, then you can of course have a typically your 12 degree in between the different connections transformer. Coming to solution, giving data, DC load current is 150 amp, DC load voltage 3 kilovolt, primary 3-phase voltage is your 440 volt, and the supply frequency 50 Hz. The total voltage across series connected diode bridge rectifier is 3 kilovolt, so the DC link voltage across single phase bridge rectifier is VDC1 equal to 3 kV divided by 5, that is 600 volt. Average voltage of one diode bridge rectifier VDC1 equal to 3 root 2 upon 5, that is PLZ. And from this we get PLZ 444.2882 volt, and the diode rating PIV root 2 VLZ, that's 628.31 volt. And second is exact transformer current, I said root 3 upon 2 upon 3 ID, that comes about 124.47 ampere, and N1 upon N2 254.04 upon 256.5 becomes 0.990355, that becomes N1 upon N3 and 1 upon N4 and upon N5 and 1 upon N6. And this is a simulated waveform, supply voltage, then the 3-phase supply current, then one converter current, the next one supply phase current, then the one converter current, and the DC link volt current and DC link volt. And coming to the supply current RMS calculation, so we have a IPPY N2 upon N1 upon IPZ and 3 upon N1 ASPZ and 4 upon N1 HZ and 5 upon N1 HZ and 6 upon N1 FPZ. The value comes 590.32 at the angle minus 2.622 ampere, and KV rating is 0.53 into VLN. Putting all the values come 460.55 kV, and the TID of primary side transformer is taking all the harmonics from 23, 25, 47, 49, 71, 73, 95, 97 by I1 square, it comes your 605%. So now coming to example 5, a 12 pulse diode bridge converter is feeding power to RL load of 50 kilowatt as shown in the figure. The input supply system is 3-phase for 15 volt 50 Hz. Consider the phase shift between the two consecutive output voltage of plus minus 15 degree with respect to the input voltage. A, the calculate the number of turns in different windings of the auto transformer for achieving the 12 pulse operation. B, the calculate the current in each winding of the auto transformer. C, the find the DC link current, supply RMS current, and TID. Calculate the KV rating of the auto transformer. So these are typically 12 pulse. Of course the interphase transformer, and phase shift of 12 pulse is 30 degree. The original supply is given to this, and plus minus 15 degree shifted here. These are typically the solution. The given 3-phase supply for 15 volt, supply frequency 50 Hz, and DC load is 50 kilowatt. So input supply volt rectifier is plus minus 15 degree phase shift. Supply voltage of VA1 dash equal to K1 VA minus K2 VB, VA dash equal to K1 VA minus K2 VC. putting the value of input and output voltage, we get a K1 solving this. K1 equal to 0.816 and K2 equal to 0.299 from the geometry, and putting a K1 plus K3 equal to 1, so K3 comes 0.184. The average output voltage of one diode with rectifier VDC equal to 3 root 6 of PA upon 5, become 560.44 volt, and the DC voltage across series connection, so it comes VDC equal to VDC1 equal to VDC 560.44 volt. This is the simulated waveform of 3-phase supply voltage, then the phase shifted voltage, then your DC link voltage, DC link current, then your 2 converter current and net supply current. So output load current or a load current ID PD upon VDC is coming 89.21, and the input diode rectifier current IL1, IL2, IL3, IL4 up to IL6 into 0.5 under root 2 by 3 ID, that comes to 36.42, and consecutive the input output equal to P in upon P out, so P in equal to root 3 BL and L. You have diode rectifier IL equal to P in upon root 3 BL, so it comes here 69.56 ampere, and I1, I4, I7 is the input current of output. So coming to INA equal to I1 69, and INA plus I equal to IL1 plus IL2, that is become 0.798 ampere, and TID of the distortion I1 11, I13, 23, 27 is and 35, 30 harmonic, and it comes 15.23%, and kV rating 0.53 into well and putting a value, it comes 41.123 kVA. Now example typically 6, a 12 pulse diode based converter is feeding power to RL load of 75 kilowatt as shown in the figure. The input supply system is 3-phase for 60 volt 50 Hz. Consider the phase shift between the two consecutive output voltage plus minus 15 degree with respect to the input voltage. So calculate the number of turns in different windings of the auto transformer for achieving 12 pulse operation. Calculate the current in each winding of transformer. C, find the DC link current, supply current, and TID, and D, calculate the kVA rating of the term. So this is typically a 12 pulse converter with the, you can call it extended for umbrella connections with the power tappings. And coming to the solution, giving 3-phase supply of 460 volts, supply frequency 50 Hz, and rotor. The input voltage of diode rectifier has a plus minus 15 degree phase from the input supply. So VA dash equal to VA plus K1 VA plus K2 VC, and VA double dash K1 VA plus K1 VA plus K2 VB, and putting the value all of these. So we get a K1 equal to 0.115 and K2 equal to 0.299 and K3 equal to 1. So from here the average voltage VDC1 3 root 6 upon 5 into VA, it comes 621.21 volt, and VDC equal to VDC1 VDC, that's 621, and output current load IDC equal to PDC upon VDC, that comes 120.73. These are the simulated waveform of 3-phase supply voltage and the phase shifted voltage. Then your typical DC link voltage, DC link current, then the converter currents, and then the net current. Coming to here, the input current of rectifier 9, all current like 9 to I9, I2, I3, I5, I8, I6, root 2 upon 3 ID, that's come 98.57, and considering the input power equal to the PO1, P in upon PO, so IL comes P in upon root 3 VLL, it comes like your 94.133 ampere, that is equivalent to I1, I4, I7, and I4 on the input current. So putting the value INA becomes minus 190.42, and INA plus IA plus I1 equal to 0. So from this IA comes here 96.29 ampere. DAD, of course, considering all I1 11 13, I13 square, it's 23 square, 25 square, 35 square, 37 divided by harmonic square under root into 100, that's 15.23, and kV rating of transformer 0.53 into VL and IN. So putting value from 70.565 kVA. So coming to example 7, a 12 pulse diode bridge converter feeding power to RL load of 25 kilowatt as shown in the figure. So input supply voltage 3-phase 460 volt 60 Hz. Consider the phase shift between the two consecutive output voltage of plus minus 15 degree with respect to the input voltage. Calculate the number of turns in different windings of the outer connection for achieving 12 pulse operation. Calculate the current in each winding of the outer transformer, and the DC link current, RM supply RMS current, and TID. So this is typically extended delta for 12 pulse plus minus 15 degree to get the phase shift of 30 degree. And these are typically the solution. So given the DC load power 25 kilowatt, 3-phase supply voltage 460 volt and supply frequency 60 Hz. The input voltage of diode rectifier has a plus minus 15 degrees phase shift from the input supply voltage of output number. So VA dash equal to VA minus K1 VBC and VA double dash equal to A plus K1 VBC. So putting all the value of phase voltage and line voltage, so we are able to get K1 equal to 0.261 and NS the ratio of short winding 1 upon sin 150 NS upon 1 sin 15. So NS comes 0.517764 and NS is the terms of long winding. So NS is equal to root 3 NS, that comes 0.8966 and then valence putting a short and long winding. So you will get a VNS equal to 137.46 volt and VNL equal to 238.11 volt. Average output voltage of 1 rectifier VDC1 3 root 6 upon pi into VLN, it comes 1197 volt. This is the typically simulated wave 3-phase supply voltage, then line voltage and phase shifted voltage, then DC link voltage, DC current, individual converter current and net converter current. So coming to DC link voltage across the series connected average record, VDC equal to VDC1 plus VDC equal to 1197 and IDC equal to PDC upon VDC, that comes 20.88 volt ampere, and the input current of direct by IA dash equal to IA double dash equal to IB dash I double dash IC dash equal to I double dash root 3 2 by 3 by DC, it comes like 17.05 plus. As considering the input of out transformer equal to P in upon P out, so P in equal to root 3 VLN, so ILN comes here putting a value 31.37 ampere, that is equal to IIC. And TAD in supply current is taking all harmonic 11, 13, 23, 25, 37 plus so square divided by I1 square under root of that into 100, 15.3%. Coming to example 5, 18 pulse ACDC diode bridge converter is feeding power to RL load of 15 kilowatt as shown in the figure. The input supply system is 3-phase 460 volt 60 Hz. Consider the phase shift between two consecutive output voltage of plus minus 20 degree with respect to the input voltage. A, calculate the number of turns in different windings of the output transformer for achieving 18 pulse operation. Calculate the current in each winding of output transformer. Find the DC link current, supply RMS current and STAD. So this is your for typically the PERC connection to get phase shift of first is directly 0 degree, another is plus minus 20 degree. With power calculation with interface transformer to connect in series. So coming to the solution, giving 3-phase supply, that is 460 volt, DC load power 15 kilowatt and supply we can say 60 Hz. The input voltage of diode rectifier has a plus minus 20 degree phase shift from the input supply voltage of down. So VA dash equal to K1 VA minus K2 VB, VA double dash K1 VA minus K2 VC, and putting the value of all line and phase voltage, we get K1 equal to 0.742 and K2 equal to 0.395 and K1 plus K3 equal to 1, so K3 comes 0.258. And now average output of burn bridge rectifier VDC1 3 root 6 upon 5 into VA, it comes 621.22 volt. And then DC link voltage across each connected bridge, VDC equal to VDC1, VDC2, VDC3, 620.22, and the IDC comes here VDC upon VDC, so it comes 24.15 ampere. These are the simulated waveform 3-phase supply voltage, then line voltage, phase shifted voltage, all 4 phase shifted voltage, then DC link voltage, DC link current, all 3 bridge current, and the net supply current. And coming to input current of all I2, I2, I3 up to I9 and IIB root 2 upon root 3 IB, that comes to 19.72 ampere. In upon P, so IL comes here 18.83 ampere, and INL plus IA equal to I1. So from this you get INA equal to minus 0.89, and typically from putting INA plus IA equal to I2 plus I3, putting a value them, it comes IA equal to 37.95 ampere. And TAD from 18 pulse, so 17 is 19, 35, 37, 53, 55, 17, 73 harmonics, divided by I1 square under root into 100, that comes 10.09%. Like. So coming to example 9, an 18 pulse diode bridge converter is feeding power to RL load of 25 kilowatt as shown in the figure. The input supply system is 3-phase for 15 to 50 Hz. Consider the phase shift between two consecutive output voltage of 20 plus minus 20 degree with respect to the input voltage. They calculate the number of turns of different windings of the output transformer watching the 18 pulse operation. The calculate the current in each winding of the output transformer, find the DC link current, supply RMS current and STAD. So this 18 pulse converter again with the power, you can call it the kind of PERC, your umbrella connection to give a plus minus 15 degree, plus minus 20 degree phase shift with one is original. And then coming to solution, 3-phase supply voltage VLN 415, DC load of 25 kilowatt and supply frequency 50 Hz. So input voltage of dash square plus has a phase shift of plus minus 20 degree for 18 pulse on the input supply voltage and transform. So VA dash equal to VA plus K1 VA plus K2 VC and VA double dash VA plus K1 VA plus K2 VB, and putting a value line and phase, we get the K1 equal to 0.137 and K2 equal to 0.395 and VDC1 equal to √3 √6 upon 5 VA, that comes 560.4 volt, and VDC equal to VDC1, VDC2, VDC3 equal to 560.44 and IDC equal to VDC upon VDC, that comes 44.6 ampere. And these are the simulated waveform of supply line voltage, then the phase shifted 3 voltage, then DC link voltage, DC link current, then 3 bridge current and supply current. And coming the input current of rectifier is I2 equal to I3 equal to I5, I7 up to I9 equal to IA, IB, IC √2 upon √3 ID, that comes 36.42 ampere. As considering the input power of transformer equal to the output, Pn equal to PO, so IL comes P upon √3 LL, that comes 34.78 ampere. And then I2 upon I2 plus I3 plus IN equal to 0, so we get IN equal to minus 68.447 and IA plus IN plus I1, that is IA, so IA comes here 70.08 ampere. And TAD here considering 18 pulse like 17, 19, 35, 37, 57 and 17, 73 all harmonics squares plus I1 is going to 100 10.09. Now coming to example 10 A 12 pulse diode bridge converter is feeding power to RL load of 15 kilowatt as shown in figure. The input supply system is 3-phase 415 volt 50 Hz. Consider the phase shift between an output voltage and the input phase plus minus 30 degree. Calculate the number of turns of indifferent winding of the outer turns of achieving 12 pulse operation. Calculate the current in each winding of the outer turns, find the DC link current and supply current and RMS current and TAD. So this is your 12 pulse with the typically extending the star connection with the umbrella kind of and then interface transformer. Coming to solution, given 3-phase supply voltage for 15 volt, DC power 10 kilowatt and supply frequency 50 Hz. So input voltage and of diode rectifier has a plus minus 30 degree phase shift from the input supply voltage up to transformer. So VA dash equal to VA plus K1 VA plus K2 VC and VB dash equal to VB plus K1 VB plus K2 VC, VC dash equal to VC plus K1 VC plus K2 VB, and putting a value of your phase voltage, getting all this, and we get the K1 equal to 0.155, K2 equal to 0.57, K3 equal to 1. So we an average output voltage of 1 VDC, VDC equal to 3 √6 upon 5 VDA. So VDC comes 560.44 and that is for all equal voltage. So output load current IDC equal to PDC upon VDC, that is 15 into 10 power 3 divided by 560.44, that's come 26.766 ampere. And input current of diode bridge I2 equal to I3 up to I11 √2 by 3 ID, that's come 21.84. Considering the input power of transformer equal to, so Pin equal to PO, that's Pin equal to √3 upon VL and IL comes here 20.86, so I equal to minus I2 minus 21.84, and taking like I1 plus IA plus small I plus capital IA plus I3, so IA capital comes I3 minus IA plus I1, it comes 22.82, and TAD comes considering 11, 13, 23, 25 and 30, 35, 37 harmonics is current square under root sum of power I1 square into 100, that comes 15.23%. And these are the references which are used to develop this lecture. Thank you.